All right, let's try this again. So what we have here is a more powerful comparator from earlier. So how can we? Why is it powerful? How can we use this to compare more number of bits? Right. So that's the question. We have the new inputs over here, right? So A0 all the way down to B3, these are the two numbers, right? So those are A3, A2, A1, A0 that is being compared with the second number B3, B2, B1, B0. So those are the things that are getting compared. So what is this? So what is A less than B, A equal to B, A greater than B input? Well, those are the things that have been compared from a previous stage. So if you wanted to make this comparison modular, then we can use these three outputs from the previous stage, and then based on the new inputs, here are the new inputs, you can generate these new outputs. Because this guy 74x85 allows you to compare two 4-bit numbers. So if you want to compare two 4-bit numbers, then you only need to use one 74x85 chip. However, if you want to compare two 8-bit numbers or 12-bit numbers or 16-bit numbers, then you might have to use many such chips. You might have to use two of these or three of these or four of these, right? Or more of these. So if you want to use more of these, where individually each chip only has the ability to take two 4-bit numbers, then you have to do it in a modular fashion, one stage after the other stage. So the previous stage comes in over here on pins 2, 3, and 4 on this chip, and then based on the new inputs, you generate new comparison outputs. And we can see this being this played out on the cascaded comparator. So what do we have over here? We have an exercise of comparing two 12-bit numbers. You can view that as maybe x11, x10, all the way down to x0. That is being compared with y11, y10, all the way down to y0, right? So if you want to compare these two numbers using this chip 74x85, which is going to only allow you to compare two 4-bit numbers, then you need three of those chips. Now notice what happens here. We are in the least significant. So here is your x, which is 12-bit 0 to 11, so 12-bit vector there, and y, the other number, which is also a 12-bit vector there. You are taking certain bits of those two numbers. So for example, here you have the 4 least significant bits, right? So here you have 4 least significant bits of the two numbers. Then you have the next 4 bits followed by the 4 most significant bits here. And clearly the most significant bits will have a say that is last, because they control whether the numbers are actually less or more or equal. So what we are doing over here is we are starting with the least significant bits, and we are comparing them 4 at a time, right? To begin with, we assume that everything is equal. And how are we assuming that everything is equal? We have connected the A equal to B input to high. So we are assuming that A equals B, which means in this case, X equals Y. We have connected A less than B and A greater than B inputs to ground, which means that these are all active high inputs, outputs, everything is active high here. So we have assumed that A equals B, or in this case X equals Y, which means A greater than B is false, A less than B is also false. Then we start comparing the new inputs, right? So we have assumed that A equals B. So this tells me, let's see, if I do this and then we say, this tells me that A, or in this case X equals Y, right? So we have assumed that. Assume at start X equals Y. Then we have these guys, A, X0, XY0, X1, Y1, X2, Y2, X0. So the 4 least significant bits of the two numbers are compared, and then that will generate, that comparison will generate the new outputs. So these are essentially your previous outputs or previous comparison status, and then this is the new. Now, based on the new outputs, those become the new inputs for the next level. So as you can see here, we are doing this in multiple stages, right? So these guys are new. I can say this is from previous stage. And all these guys are the new inputs, which in this case are the four bits in the middle, right? So you have 4 least significant bits, 4 most significant bits, but you also have the 4 bits in the middle. There's a question in the chat box, which is, by previous, do you mean less significant? So when I say previous stage, I mean this stage. We can call this stage, let's see, I can call this maybe stage 1, stage 2, stage 3. So when I say previous stage, I'm referring to the comparison that happened earlier, which was stage 1. And in this case, it happens to be the 4 least significant bits. But if you look at it from the perspective of stage 3, it is not the least significant, it is just the least significant bits with respect to stage 3. So the inputs to the stage 3 are coming from stage 2. So the question is, will the new inputs, the comparison of the new inputs, will they override the previous stage or not? That's exactly what happens. So when you compare the new guys, let's say X4 all the way to X7 and Y4 all the way to Y7, based on how they compare, the new outputs that will override previous one, override previous. So suppose, what I mean by this is this. Suppose based on this comparison, A is less than B, right? A is less than B. If A is less than B and earlier AX was equal to B, A was equal to B, then because the new inputs suggested A is less, it will override whatever came from earlier, the previous comparison. I hope that is making sense. It treats the inputs from the previous stage as a tiebreaker. Yes, absolutely. So if it is, if earlier it was equal and here it was greater, then the new outputs will be greater, not equal, not less than. And of course, the outputs are in such a way that they are all mutually exclusive. Only one of them can be active. So it is treating the previous stage as a tiebreaker, absolutely. But the new inputs, the higher level inputs, the more significant inputs will have override power in this case. And similarly, the last stage, stage 3, will get inputs from the previous stage, which is stage 2, but depending on the new inputs, which in this case are the 4 most significant bits, that will override the previous ones to generate new outputs, which will let us know whether a is less than y, where x is less than y, x is equal to y, or x is greater than y. So, just to recap quickly, you have 12 bits each for x and y. You have given 4 least significant bits of each number here. The next 4 here, the 4 most significant bits to stage 3. Then each 74x85 chip has 3 inputs indicating whether the numbers are equal or not, greater than or not, less than or not from the previous stage. And we are assuming that at start they are all equal by making those connections to power and ground. And then based on the new numbers, you generate new outputs. And that keeps moving forward with the idea that the previous stage, because it is lesser in significance, it will be overridden by the newer, higher significant bits. How they compare. All right, so that's essentially how a cascaded comparator works. So we have taken a 4-bit comparator and we have made it into a modular 12-bit comparator. There's another question in the chat box, which is, but is stage 1 and 3 is equal and 2 is not equal, the output is x equal y. No. So if these things are equal, and if so, Palin, if stage 2 the output is greater, then this guy will be active, right? So if this guy is active, this guy is active. And over here, if these are equal or not, because a greater than b will take into effect. You guys see that? Yeah, in that case, the output will be output of the previous stage. Yes. So the most significant bit, if it is equal, then if it looks for whether a was less or not from the previous stage. All right, let's move on to something that we have seen earlier, very informally now. So if you take a look at this 8-bit comparator, the 74x682 chip, there were only 2 outputs, equal and greater than. Now, clearly, if both of them are false, and because these are active low outputs, both of them false mean 1, 1, then P will be less than Q. In other words, you can derive this new P less than Q comparator output using P equal and P greater than Q outputs. In fact, you can derive all the others. So all 6 of them, all you would need is equal and greater than. So if you have those 2, you can derive all the others. And the way we do that is simply by having some simple logic between the 6 outputs and the 682 chip. So the 6 outputs, the most crucial ones are equal and greater than, because using these 2 you can derive everything else. So equal is right here, greater than is right here. So those 2, using those 2, you can derive everything else. So let us take a look at some of the outputs. If you look at P not equal to Q, how do you know whether P is not equal to Q? Well, it is simply the complement of P equal to Q. So you just take a look at this. We have connected it directly to P equal to Q, but because this is active low output, P not equal to Q becomes a active high output. So this becomes an active high output simply. That's it. But they are the same wire. How about P equal to Q? Well, P equal to Q, which is an active high output for equality, that is simply a NOT gate. So that bubble cancels out with that bubble, and then you get P equal to Q. In this case, it was active low. Over here, it is active high. How about P greater than Q? Well, again, take pin number 1 here, active low, complement it, you get P greater than Q in active high format. So all these are active high outputs. Over here it was active low and active low. How about P greater than or equal? For greater than or equal, you have to take P equal, P greater than, complement both of them, and then put a OR in front of it. So essentially what you're doing is you're taking P equal to Q, which is in the active low format, and you are complementing it, or P greater than Q, you are complementing it twice again. That will be essentially P greater than Q, greater than or equal to Q. So that's how that is related. And again, that's the active high output here too. P less than or equal. Well, for P less than or equal, you can just take P greater than or equal and flip it. You get P less than or equal, right? P less than or equal to Q equals the complement of P greater than Q. That's it. And again, active high. And for P less than Q, you take the two outputs, P equal to Q complement, and it with P greater than Q. So I can write that as P less than Q equals P equal to Q, which was in active low format, and P greater than Q, which was also in active low format. So this can be written as using De Morgan's law. We can write that as P equal to Q nor P greater than Q. That's what we had earlier when we were writing the expressions. So all outputs are over here active high. The two outputs from the chip are active low. So this is a quick discussion about how you can use some logic gates in front of this 682 chip to derive all the 6 outputs in active high format using only 2 outputs from the chip, which are in active low format. All right, questions about this slide, slide number 30. All right, so let's now focus on adders. And there are 2 adders that I'm going to go over. The first one is a full adder that you guys looked at in Studio 3, I believe. And actually in Studio 3, you did a 4-bit full adder. So some of the discussion over here is going to be a little bit simple, and then we will expand on that in order to make the adders very, very fast. So let's see. We have a 1-bit wide adder, which is, say, instead of 4-bit, let us say we start off with the 1-bit full adder. We were calling that bit full adder, right? That's what we called it, 1-bit full adder. So if you want to have a 1-bit full adder with inputs X, Y, and Cin is essentially the carry from previous, right? Carry from previous addition. X and Y are the new numbers. Cin is carry from the previous addition to generate new outputs. Those are sum and carry out. So based on X, Y, and Cin, which are essentially your inputs, you can have 8 different combinations. Based on those 8 different combinations, you can write out what should be the sum and what should be the carry out for those 8 combinations. So carry out, this will be what? Carry to next addition. So for example, if you had something like this, say you had, I can use A3, A2, A1, A0. We were using X earlier, so let me check X. I'm representing this number X in this format: X3, X2, X1, X0, and I'm representing Y as Y3, Y2, Y1, Y0. Now, when you start adding these, what happens? Initially, what do you assume? You assume in the case of addition, you may assume that initial carry is 0, right? So you might say C sub 0 is 0. You might assume, or non-zero, whatever that is, there is some initial carry. Then you add them up to generate S0 and C1. Now let's focus on this. Let's focus only on this part. If you focus only on this part, can I say that I will not be able to carry out the next addition until I actually find C1, right? I will not be able to carry out the next stage addition unless I know C1. And similarly, X1 plus Y1 plus C1 will give me S1 and C2. That will be my next stage. I cannot add X2 to Y2 until I have C2 ready, which C2 comes from the addition of the previous stage. So notice what is happening here. The problem that is happening here is even though you have even though we have X comma Y readily available, you are adding the two numbers, right? So those numbers should be given to you. Those are ready all the time. They are available right from the beginning. Even though we have those two readily available, addition is slow because we need to wait for carries. Carry is what? From previous stage, from previous addition operations. I wouldn't call it transmission delay because this is we are not trying to transmit the bits. We are just adding the bits, right? So there is a delay, and that delay has to do with how this adder is constructed. This adder is constructed based on a Ripplecarry addition format. Now, if you focus on why is this called Ripplecarry? Because the carry is rippling through this addition, right? So from here to here, the delay is from here to here, from delay is from here. The carry is rippling through the addition. And because of that rippling effect of the carry, not for the inputs X and Y, not for the sum, it is the carries that are the bottlenecks. Right? I cannot do X1 plus Y1 because I need to wait for C1. I cannot do X2 plus Y2 because I need to wait for C2. Nothing else, only C2. And similarly, I still need to wait for C3 over here. And then eventually I will generate C4, but that is not important for me. I need to wait. Where do I need to wait? I need to wait on C1 then I need to wait on C2, then I need to wait on C3 to be able to do that addition, right? That is called a Ripplecarry adder. Now, clearly, if I had 8 bits to add, or 12 bits to add, or 16 bits to add, my Ripplecarry adder delay, or the time it takes for me to complete the addition, will keep on increasing linearly with the number of bits. So let us see how that actually works out. But before we do that, I hope you understand one thing, which is C out refers to the carry to the next stage, and C in is the carry from the previous stage. So I'm going to start writing this using the index of the bit position, just as I did over here, x0, y0, x1, y1. I was using the index for the bit position, right? So for C out and C in, what should I use? For C out, I will call that Ci plus 1, indicating that it is the output to the next bit position, like. And for C in, I will use Ci. So for example, if Ci is 0, if I is 0, you get 0 and 1 here, right? 0 and 1 here, and so on. So C out, I'm going to call that Ci plus 1, where I is the index of the bit position being added, and C in, I'm calling that C sub I. That is the index being added right now. And if I choose that I as the index, I also need to choose x sub I and y sub I and s sub I, right? So x sub I, y sub I, and s sub I, those are all the numbers and the output sum for the ith bit, right? For the ith bit. And this goes back to the full adder studio block diagram that you did. You used C0, X0, Y0 to generate S0 and C1, Ci plus 1. Now, can I write, based on this truth table, can I write an expression for maybe sum and carry out? I can quickly write those expressions out. So let's try to do that over here. Ripplecarry adder. So this is still a Ripplecarry adder, also called as the slow adder. And I'm trying to write expressions for sum and carry out. So S sub I, the sum at any ith position, can be written as x sub I exclusive or y sub I exclusive or C sub I. And you can verify this later on whether this is actually correct or not. You can verify that. So sum at the ith position is related to the numbers and also to the carry. I do not need to wait for the numbers. Those are readily available to me. But I need to wait for the carry, which is the bottleneck. So let us turn our attention to the carries, Ci. So Ci plus 1 can be written as x sub I and y sub I, or x sub I, let's see, C sub I, or y sub I and C sub I. So this is a sum of products expression, SOP expression. Where did I get that from? We had a truth table for the Ripplecarry adder, and from the truth table I translated that logic into a logic expression for sum S sub I and C sub I plus 1. This is as simple as taking these once, right? Or you just use k-maps, right? So we don't need, so use two 3-variable k-maps. Why do we need two? Because there are two outputs, sum and carry out. So if you use two 3-variable k-maps, it will turn out that sum s, you will not be able to combine the ones, and you will have to write them individually. So these guys will have to be written individually. But if you use some Boolean algebra to represent it in a exclusive OR gate form, you will see that the expression that I wrote will be correct. But for carry out, you can combine the ones, and when you combine the ones and simplify and write the expression in terms of x sub I, y sub I, and c sub I, you will be able to write c sub I plus 1 in that particular format. So that is the Ripplecarry adder. Let us see. Now clearly, if I'm waiting for c sub I plus 1, I need to wait for c sub I, right? I would need to wait for I minus 1. I minus 1, I would need to wait for I minus 2, and so on, right? So that ripple, that carry will always slow me down, right? So the problem here, let me write down the problem here. Problem with Ripplecarry adder is long delay, as carry bits ripple through from least significant bit to most significant bit. Now, if I asked you guys, what is the gate delay? So use the term gate delay. What is the gate delay? Gate delay is the delay for one gate, AND gate, OR gate, whatever that might be. One gate delay means that there is one logic gate involved. So what is the gate delay to compute C1? That is the question. What is the gate delay to compute C1? What is C1? C1 is x0. You see this? I'm just using that guy. x0, y0, or x1, x0, c0, or y0, c0, right? So how many gate delays are involved in this? 2 gate delays is absolutely right. Why? Because it's an AND OR circuit. SOP. So first you do AND, 1 AND, 2 AND, 3 AND, followed by 1 OR, right? So you have AND, corresponding to AND, and then you have the OR. So there are 2 levels to this circuit. So there will be 2 gate delays for this. All right, so my next question is, if there was 2 gate delays involved to compute C1, how many gate delays will be involved to compute C4? So in order to add 4-bit numbers, I need to go all the way to C4. How many gate delays will be involved to compute C4? Alex says 8. So I'm going to add up like this. You see, 2 gate delays 4, 6, 8. So there should be 8 gate delays involved. For 4-bit addition, 8 gate delays. This is only for carry, by the way, right? We only worry about carry, because if we had carry, right? If we had carry, we already have X and Y, and we would be able to generate S sub I very, very quickly. So, we don't need to wait for X and Y. We only need to wait for carry, right? So that's why we are trying to focus on carry. Now, let me ask you this. When you were considering only 1 bit, you had 2 gate delays. When you went for 4 bits, you had 8 gate delays. Using this, can you guys tell me gate delays to add n bit numbers? How many gate delays would it involve for n bits? 2 times n is absolutely right. Now, what is the problem with this? The problem is gate delays depend on n, the number of bits in the numbers, right? So if I go to 8-bit addition, I will have to wait for 16 gate delays. If I go for 64-bit addition, I will have to wait for 128 gate delays. That is extremely bad. Why is it bad? Because it will make things slow if you have a bigger number larger number of bits to represent the number. And you would need more number of bits to represent the number, because more number of bits mean more precision in the number, right? So if you want more number of bits, if I'm not able to add them very quickly, then at a very, very basic operation of addition, I am being very slow. So that's not good. That is a slow adder. Hence, we need to worry about how to reduce this gate delay. So that's where we are going next. Reduce this delay using carry lookahead adder, CLA. And the name gives it away, right? We are looking ahead for carries. We are computing carries first ahead of time so that we don't have to wait for them. In other words, we want to make this gate delay independent of n, right? So this n, that is the problem. We want to make the gate delays independent of n. So it should take the same amount of time, or in theory, it should take the same amount of time to add 4-bit numbers as 64-bit numbers. That would be really, really good, right? In theory, we should be able to do that, but if we had all the carries computed ahead of time. And we can do that, but we have to play a little trick. So let's take a look at the carry lookahead adder. Let's see. So here, that is a schematic of the full adder circuit that you guys have seen earlier. This is sum and carry out. This is for each bit position, right? So that's the bit full adder, 1 bit full adder. You guys have seen this in studio. You guys have seen this in lecture. So I don't think there is anything new here. So we have looked at the expressions as well. We are just writing this. We are just drawing the logic diagram for this over here. And again, C out is 2 gate delays. First level, all of them happen at the same time, and then the second level. for some, because it depends on carry in from the previous stage, we need to worry about the same thing again, C out. This is the the block diagram of the Ripplecarry Adder. You guys have seen this in the Studio 3. There's nothing new there. The speed is limited by the carry chain. We established that when we were having this discussion. And fast adders, or the carry lookahead adder, that limits the carry chain. We will try to compute the carries ahead of time. So let's try to do that. Now, in order to do that, I'm going to use the same expression that I had earlier. What is that? I had, let's see, this is carry lookahead adder now. And I'm going to use the same expression that I had earlier. I'm going to simply copy this guy and paste it over here. All right, so I start with this carry, right? And I'm going to do some algebraic manipulation here, which is I'm going to define that x I and yi is defined as g sub I. And for the next one, I will pull out a ci, which is a common factor between the second and the third term here, to get x sub I or y sub I. And I will define this as p sub I. So I'm introducing two new functions here, g and p. G sub I is called the generate function. Why is it called the generate function? It is called generate function because g sub I equals 1 directly generates c sub I plus 1 equals 1, regardless of the previous carry, right? So if g sub I is 1, it generates the next carry as 1. C sub I will be 1 regardless of c sub I, right? Because it is g sub I plus something. So this or this, if one of them is true, the overall thing is true. That's why it's called the generate function. The next function is what? P sub I. It's called the propagate function. Why is it called the propagate function? Because if P sub I is 1, then C sub I equals 1 will propagate to C sub I plus 1 equals 1. In other words, if C sub I is 1, then propagate P sub I 1 will propagate to C sub I plus 1. Now, once I have defined these two guys, G and P, I will write a new expression for C sub I plus 1. C sub I plus 1 can be written as, in a very compact manner, I can write that as G sub I, P sub I, C sub I. Do you guys agree with this so far? Just defined G and P as propagate and generate functions, because they are defined as generate and propagate because of what role they play in the expression for c sub I plus 1. But you know, there's another another reason why they have been defined this way. The main reason is this. The main reason is g sub I comma p sub I are independent of carries, right? That's the main reason here, that for which we isolated them into those two functions. And g sub I is x and y, p sub I is x or y, right? So it's independent of c sub I. In other words, that's not the bottleneck. G and P are not the bottleneck. So what can I do with this expression? I can play a little algebraic trick with that expression. If C sub I is G sub I or P sub I, C sub I, can you guys think about writing an expression for C sub I? All you have to do is subtract 1 from bit index. What do you get? C sub I will be G sub I minus 1, the previous generate function, or P sub I minus 1, C sub I minus 1. Let us write this as equation 1. This is equation 2. Substitute equation 2 in equation 1. What do you get? Substitute 2 in 1. So we are substituting for C sub I. What do you get? You get C sub I plus 1 equals G sub I remains as is, or P sub I multiplied by C sub I, which is the new expression. G sub I minus 1, P sub I minus 1, C sub I minus 1. All of that is in blue. You guys okay with this so far? Because this particular substitution step, we are going to keep expanding now. We are going to keep doing this substitution. So I want to just take a moment here to see if you guys are able to follow this so far. Okay. Now let us write now what do you have? G independent of C, P independent of C, G I minus 1 independent, P independent, C I minus 1 is the culprit now, right? So C I minus 1 should be attacked. So let's write C I minus 1 equals what? Subtract 1 from the bit index again, right? So what do you have? G I minus 2, P I minus 2, C I minus 2. So this is, let's call that equation 3, and the way we got that is, again, subtract 1 from bit index. Copy, paste. And we did that on equation 2. Which means I can again substitute this guy over here. So what do I get? I get Ci plus 1 equals Gi or Pi. Actually, let's write it this way. Gi P Gi minus 1 or Pi minus 1 Gi minus 2 Pi minus 2 Ci minus 2. So if I expand everything out in a sum of product form, what do I get? I get Gi or P sub I G sub I minus 1 or Pi minus 1 Gi minus 2 or Pi minus 1 Pi minus 2 Ci minus 2. The only problem with this expression right here, Ci minus 2. So that means that if I were to continue to do this expanding, right, keep subtracting 1 from the index, do a substitution and keep expanding, then I can reach to the smallest C sub I minus 2. What is the smallest C sub I minus 2? The last one. The last one should be C sub 0, right? That is what is the smallest carry, initial carry. And if I was able to do that, what are you going to have? You're going to have a bunch of terms with G and P that are independent of carry, but only the last term will depend on C sub 0. So we are trying to move towards an equation that will be independent of the number of bits. So let's try to do that. I'm going to write that on the next slide here. I will say keep telescoping, meaning subtract 1 from the index and do a substitution. And we can get Ci plus 1 in terms of Gk and Pk, where k is the index, right? I minus 1, I minus 2, and so on. So G's and P's, where k is equal to 0 to I. But that expression for C sub I plus 1 will also depend on C sub 0. And that means that there's no propagation delay for this, right? For C sub 0, there's no propagation delay. So let me write down the final form here. If you keep doing this telescoping, keep expanding, you will get an expression like this. Ci plus 1 equals Gi or Pi Gi minus 1 or Pi minus 2 Gi minus 2, or keeps going. And then you will have Pi minus 1, product, P2, P1, G0, or Pi minus 1, product, P1, P0, C0. So that will be the overall expression. I'm using ... because the index will keep going down, wouldn't it be pi minus 1, gi minus 2? Where is that? Yeah, I said gi minus 2, right? The third term is gi minus 2. Oh, p, you're right. This is pi minus 2 here. I minus 1, yes. You're right. All right. So now if you ask the question, what is the problem with this? Where is the bottleneck? The bottleneck is C0. Well, not really a bottleneck. Why? Because no propagation delay for C sub 0. That is initial, that's the initial delay. So there's no bottleneck there. We have made things independent of n. So let's try to actually find out how many gate delays are involved. How many gate delays are involved with respect to C sub I? Well, C sub I plus 1 is in the SOP form, right? And if it is the sum of product form, we know that it involves 2 gate delays. Yes. However, the generate function is also there. The propagate function is also there. So the generate function requires 1 additional AND gate. The propagation function also involves a 1 additional OR gate. That AND and OR function can happen simultaneously. So that goes from 2 to 3 gate delays. So 3 gate delays for the carry C sub I plus 1. So that's the result, right? So let me write down the result. The result is SOP form. So just 2 gate delays. For every C sub I result, independent of n, including C sub I plus 1. Including C sub n, the most significant. So this is most significant carry. We need one more gate delay to generate P sub I and G sub I, and one exclusive OR gate to generate S sub I. So what is the total? Total would be 4 gate delays. 4 gate delays to do the entire addition. Exclusive OR for the sum is included, generate propagate functions are included, the carries are included, all of them. 4 gate delays for everything. The best news is it is independent of n. So earlier we had dependence on n, now we have independent of n, but there is one problem here. The problem, we have to give up something to gain this, right? What is the thing that we gave up? Mainly we gave up this. You see, to generate C sub I plus 1, what do you have? One term, 2 things getting ANDed, 3 things getting ANDed, 4 things getting ANDed, so on. If the number of bits in the numbers, 12 bit, 14 bit, and so on, if the number of bits, if n increases, the fan in of these AND gates will keep on increasing. So fan in is the problem here. So the problem with carry look ahead. CLA is it is going to be a massive logic circuit. But the main problem is going to be large fan in. And because of the large fan in, we can also no longer make it modular. Because it's a very, so there will be a fan in limit, which means that I cannot do 12-bit addition or 32-bit addition all using this. So it's no longer going to be modular, which means that I will have to use smaller carry look ahead adders to make bigger carry look ahead adder. So I'll have to use some sort of a modular look ahead carry look ahead adder. All right, so that's essentially how you make a fast adder. All right, let's move on here. All right, so that's the basic idea. Calculate the carries quickly and then feed it into the adders in parallel. That's what we are doing here. And all the idea here was represented using logic expressions earlier. We used all the inputs x sub I minus 1 all the way down to x sub 0, y sub I minus 1 all the way to y sub 0, and c sub 0. And here is where we did the carry look ahead or adder logic. What was that? The generate function, the propagate function. We did that, followed by the ANDing to come up with c sub I. Once we have c sub I and s sub I from the half adder here, you generate s sub I for the overall carry look ahead adder. Now, because we have the logic expressions for generate function, propagate function, and for the sum, by using those expressions, we can sketch things out using logic gates. So over here, we are essentially translating the expressions that we wrote into a logic gate format. One thing that I would like you to note here is the number of inputs. If you keep going up, I hope you see that there will be an increase in the number of inputs. 2, 3. If you keep going up, right, for more and more bits, the fan in will keep increasing, which is the problem here. But all of these logic diagrams can be traced back to one entity, which is right here. This is the most important result. And as you plug in I equals 0 and 1 and 2, you will get all the corresponding logic diagrams that you see in that slide. All right. Let's move on to, so here is the complete carry look ahead adder. This is the 4-bit adder. Earlier we were just showing part of this, but again, 2 inputs, 3 inputs, 4 inputs, 5 inputs. So the fan in keeps increasing, which is the problem with the carry look ahead adder. Because we want to do it very quickly, fan in will increase. Also, the number of gate delays, right? They will be constant for no matter how many bits you have. Now, if you want to make this into a 16-bit adder, over here, as you can see, this is 16 bits of X added to 16 bits of Y. we are essentially using 4, 1, 2, 3, 4. We are using 4 74x283 chips. 74x283 chip is this. It's a 4-bit carry lookahead adder. So by using 4 of those and by daisy chaining the carries, so between each stage you are doing a daisy chain for the carry. Let's see, come on. Right here, this guy is daisy chained to this. That's it. This is the final carry. So I can say daisy chain carries from each chip. So those are the only things that are rippling through, right? So there is a ripple carry between the groups. So that takes care of the fan-in problem, right? Because even though we are only adding 4 bits here, 4 bits here, 4 bits here, 4 bits here, because we have kept it only to 4 bits and not made it into 16 bits, still the fan-in is manageable for each chip. And the only way to connect them to make a 16-bit adder, the only way to do it is to ripple the carries between those groups. All right, so I am going to stop here. I've already taken too much time from you guys.